Mathematics. Y, for a right-angled triangle, is the square of the hypotenuse equal to the sum of the squares of the other two sides. Why? Almost everyone learns that c squared equals a squared plus b squared. But why does it? Asking why is asking for the explanation. In mathematics, explanations often involve a particular structure or process, and that process is known as proof. There are many proofs of the Pythagorean theorem. Some are algebraic and begin with axioms, others are geometric, some graphical or even animated. A book exists containing 367 different proofs of the theorem. In all cases, the proof constitutes the mathematical explanation. Proofs exist so one can be shown, which is to say, understand why c squared equals a squared plus b squared for a right-angled triangle. But proofs start somewhere. They begin with axioms. Axioms are things not proved. They are what is assumed true, and indeed are sometimes simply called the assumptions. On what basis can we assume they are true? Many arguments are put forth here, often coming down to, it is self-evident. It couldn't be otherwise. A fallibilist might say, well, we do not know they are true, we just assume, tentatively, they are. Or perhaps we just say, they are the knowns. They are what we know now, and we also know the rules of inference, and together we can see where they lead, to what conclusions or theorems. In a worldview that values explanations, we might even say, the axioms are what they are in mathematics because no explanation is ever improved by changing any of them. Those axioms themselves constitute explanations of a kind, claims about reality. Not certainly true, but representations of necessary truth. We are, all of us, fallible, even mathematicians. Mathematics commands a special place in academia. Traditionally, it is the subject to which all others have aspired. Mathematics, it has been thought, are where we finally get to so-called epistemological bedrock, some certain and absolute truth where all doubt is removed. Science can only aspire to such lofty heights, for science relies on evidence, open to interpretation, and, so it is said, only the accumulation of sufficient amounts of it can ever make us confident our theories are true, or probably true. As for philosophy, and everything else, mere matters of opinion, of course that entire hierarchy of mathematics as certain, science as probably true, and everything else as more or less a matter of opinion is itself not a mathematical claim, it's a philosophical one. Instead, mathematics is better understood as distinguished by its subject matter and method. That method of mathematical proof does not mean show as true. What it means is calculate or compute what follows given some axioms, using some rules of inference. Mathematics is about explaining necessary abstract truth. But as David Deutsch wrote in The Fabric of Reality in his chapter on mathematics, quote, necessary truth is merely the subject matter of mathematics. It is not the reward we get for doing mathematics. End quote. In a sense, much of what David Deutsch is famous for itself proves that very conclusion. In laying the foundations for quantum computation, David proved what was then sometimes called Turing's thesis, which may be expressed as every physical process is computable. That implies anything in physical reality can be simulated by a computer, from atoms to weather systems, galaxies, even in principle a human brain. David Deutsch took the thesis and, on the assumption of quantum theory, proved it. After all, computers and brains are not abstract objects. They are made of matter, matter obeying laws of physics, laws of quantum physics. So now many call it the Church-Turing-Deutsch principle, to distinguish it from a mere thesis of pure mathematics. It is now properly regarded as part of physics, a principle governing the behaviour of all physical objects, and that includes brains, like the brains of mathematicians. The laws of quantum physics say we can never rule out the possibility of something unexpected happening. This is otherwise explained as there is always subjective randomness. In other words, you cannot know the outcome exactly of any physical process. There will always be uncertainty, a range. This applies to brains, classical and quantum computers, any process. It applies to what mathematicians do. Quantum theory mandates we can never know with absolute mathematical certainty that a particular outcome must happen. There is always a range. However small the chance of error, It does not matter. It is not zero is the point. So physical systems evolve in ways we cannot know for sure. And that includes brains and the outcomes of any computation. And mathematical proof constitutes a computation and therefore cannot confer upon its conclusions absolute certainty. Not only because we cannot know for certain the axioms are true, but because the process itself of mathematical proof is a computation. Computations are done by computers, and computers obey the laws of physics that rule out knowing for certain that something unexpected did not just happen during that proof. Mathematics is the study of necessary truth. It constructs knowledge of necessarily perfect abstractions, but the knowledge of that perfection is not the perfection itself, any more than knowledge of electrons is electrons, or knowledge of birds is birds. We are fallible, and knowledge is imperfect, even in mathematics.